Welcome. In this video, I will show you how to measure a magnetization curve of a bulk material using a ballistic method equipped with a permeameter. Typical samples for this kind of measurements come in form of bars whose aspect ratio must be approximately 10 to 1, so the length must be approximately 10 times the diameter. For this specific sample, the length measured with a long-range gauge is approximately 200 millimeters. On the contrary, the diameter that must be measured in different positions is a little bit less than 10 millimeters. While the measurement of the sample length is not extremely important, the determination of the sample diameter instead is critical because we will need to calculate the sample cross-section, especially in the center position, where pickup coils will need to be installed. The pickup coil is realized with a very thin insulated copper wire. In our case, its nominal diameter is 0.05 millimeters, but after measurement with the gauge, it turns out to be 0.06. It is important to know the diameter of the wire with which you prepare the coil, because the actual cross-section of the coil will be the cross-section of the sample plus the thickness of the wire. This means that the pickup coil will pick not only the signal coming from the sample, but also from the thin layer of air surrounding the sample due to the thickness of the wire. It is therefore needed to know the correct diameter of the wire in order to be able to compensate for this contribution of air. The coil consists in 5 turns of the wire that are closely packed together and placed very close to the center of the sample. With some scotch tape, we keep the 5 turns close together so that they do not move. When the coil is complete, it is necessary to twist the excess copper wire so that you do not obtain parasitic turns that could pick some signal, undesired signal, when the magnetic flux changes in the permeameter. It is necessary to twist the excess copper wires for a length of several centimeters in order to be sure to be out of the region where the magnetic field changes. At the two ends of the copper wire, we prepare two tiny loops that are then coated with tin. This will help to ensure good electrical contact between the pickup coil and the contacts on the permeameter. It's a good idea to check that the wire is not broken and that it is not short-circuited to the sample. The sample is now ready to be measured with a permeameter, which is an incomplete iron yoke. The sample will complete the closed magnetic path when it is inserted in the proper way into the permeameter. The ferromagnetic yoke is equipped with adapters that can accommodate samples of different shape. In particular, there are adapters for flat samples, such as sheets, and for cylindrical samples, such as the bar that we are measuring today. These adapters must be inserted in the proper position on the left and right of the yoke, so that the sample can be placed in the middle and can ensure a repeatable and efficient closure of the magnetic flux in the yoke. The sample must be inserted with the pickup coil approximately in the center of the gap of the permeameter. The free ends of the wires of the pickup coil will be clamped into the permeameter. The polarity is not important. The signal measured by the pickup coil will go to the flux meter. The flux meter is periodically checked with a calibrated mutual inductance of known value. To measure the magnetic field to which the sample is submitted, we use a Hall probe, a commercial Hall probe, whose sensing element is extremely tiny and is placed at the tip of the probe. Each Hall probe has a different and specific calibration constant. If the gauge meter does not read it automatically, it must be manually set on the instrument before performing any measurements. Then the probe must be zeroed, preferably with a double-shielded mu-metal null chamber. The probe is placed in close proximity of the sample at the center of the permeameter gap and very, very close to the position where there is the pickup coil. We can now clamp the sample to the magnetic yoke to ensure a good flux closure. The gap should be as large as possible, taking into account that high-intensity fields require narrower gaps. The system, both the power supply of the yoke and the electronics, can now be powered on. The power supply operates at constant voltage. In order to control the magnetic field, we can act on a bank of resistors. These are variable resistors connected in series with progressively decreasing in values. By regulating them, by increasing or decreasing them, and so by increasing or decreasing the total resistance of the circuit, we can control the current that flows in the yoke, and so we can control the magnetic field. The magnetization curve is measured one point at a time. As an example, our first field point is of the order of 400 Ersted. So we regulate the current that flows into the yoke in order to reach the desired field value. The flow meter, since it is an integrator, is subject to drifts. For this reason, it is important to compensate for these drifts in order to have a stable measurement. Given the magnetic field that has been set in the previous step, the measurement is done by inverting its sign several times through a relay. With the flux meter, we measure the flux change associated to each reversal of the magnetic field. The flux meter is zeroed at each step. The measured flux variation at the desired field value is recorded in a table. We can then repeat the same procedure for all the other desired field values. The field is set, then the flux meter is zeroed, and the sign of the magnetic field is reversed several times in order to measure the flux change, that is averaged and then inserted into the table. Now we have all the ingredients to calculate the magnetic induction of the sample. We know that the magnetic flux that we measured is the product of the magnetic induction times the cross-section. Indeed, the cross-section is something a little bit more complicated because, of course, we have the cross-section of the sample, but we also have the wires forming the pickup coil around the sample that have a finite thickness, so we must take it into account. Also, we do not have just a single coil, but we have a certain number n of coils, indeed 5 coils, so we must take that also into account. And then, when we integrated the flux change, we integrated it from a positive magnetic field to a negative magnetic field, or the other way around. So indeed, the flux variation is twice as much what we must take into account. So the final formula for calculating B is the one shown here. Now, which cross-section should we consider? Of course, we are interested in the sample cross-section. The sample is the gray object that you see in the slide. But we must take into account that what we have measured with the flux meter is the sum of the sample and of the cross-section taken by the pickup coils, which includes the wire's thickness. We have measured the sample diameter with the gauge at the beginning of the experiment, and we know also the wire's diameters, which, as you can remember, is 0.06 millimeters. So we can calculate both the sample cross-section and the total cross-section. And we must calculate a correction factor that takes into account the fact that there is some flux taken in air by the pickup coils, which cover a diameter that is larger than that of the sample. To summarize, first we calculate the induction using the cross-section of the sample. Then we calculate the correction factor that takes into account the finite thickness of the wires of the pickup coil. And finally, we calculate the induction of the sample, both in terms of V and J, and if we want, also the permeability. Now we can enter all the data in the spreadsheet where we have already set up the necessary formulae. In this demonstrative video, we just acquired 3 measurement points of induction as a function of the applied magnetic field. But in principle, point by point, you can construct a whole magnetization curve and, with a slightly different procedure, even a hysteresis loop. Among the strengths of the ballistic setup is there's the possibility to work with different magnetic field sources. This solenoid, for example, is used for measuring the magnetization curves of samples that are not magnetic. The samples, again in form of bars, if placed close to a compass, do not move it, meaning that they have a very low magnetization and a very low permeability of the order of the unity. In this case, the pickup coil is not directly wound on the sample. Instead, it is fixed in the center of the magnetizing solenoid in correspondence of that blue band that we can see from the outside. An external compensation coil allows to null the signal of the pickup coil when no sample is inserted into the solenoid. The sample is placed inside the solenoid at the central position, so that the pickup coil is approximately at mid-length of the sample. When using this solenoid, Instead of measuring the applied magnetic field directly with a Hall probe and a gauge meter, we use a different system. We measure the current that flows into the solenoid and use its calibration constant to calculate the applied field. We have the possibility to connect in series to the solenoid a calibrated resistance of known value. The jumper is removed, and the current is measured across a calibrated resistor connected to a multimeter. The measurement procedure does not change, but we can obtain with this system permeability values close to that of air. The same ballistic method can be used with an even different magnetizer, the so-called Epstein yoke. It is a square frame with both primary and secondary coils, so both coils for generating the field and picking up the signal, where sheets of cut with a standard length and shape can be inserted in a specific way, following their lamination texture and making multiple turns with a minimum mass or minimum number of turns defined by the standard. The Epstein frame can be made with coils with fewer turns and a smaller gap when measurements instead of DC conditions are done in high frequency. In any case, at the corners where the sheets are joined, blocks of known masses are used to ensure a good magnetic flux closure across the sample. The measurement technique with the ballistic method remains all the time the same, independent on the magnetizing device and on the material under study.